So hi everyone, I'm Aviad. I was working this quarter with Zara, Paul, and Emily, and Greg uh, to make the improvements we want to make for TRON. We want to call it TRON Plus. Um, so a little bit of like overview, like why overview of the presentation. So I'm going to go over motivation, goals we had for the quarter, the problems we were dealing with. That is two main problems: the calibration process and the continuous module of TRON. What we currently have with TRON, what approaches we took, comparison, and what we want to do forward. So the motivation, like the bigger picture for RPOD, we're all familiar with that. So space sustainability, we have increasing number of objects in orbit around Earth. This is in the last 60 years, and it is predicted to grow even more. Then space logistics, they require high levels of autonomy. So we want to be able to achieve those complex missions and mitigate real-time risks. So kind of zoom in into the motivation for our TRON testbed. We want to conduct hardware and software in the loop simulations. We have obviously limited access to space, and we want to enhance the reliability and safety of space missions. And that can be done with software and hardware in the loop and validation of algorithms on Earth here before we send them to space and potentially lose a lot of money. And then we also, so with the rise of AI and machine learning models, we want to have the capability here at Slab to generate data for data-driven models and methods. So the goals for the quarter was learn a lot about TRON procedures. This is a big goal by itself. It is a long process, but we learned what we needed to learn. Recalibrate the robot's absolute position to have even more accuracy in what we have in the past. That is with the help of Robotic that Professor D'Amico hired to help us. Regain some of the TRON capabilities that the lab somewhat lost when Jeff, the previous expert on TRON, left. And there was remounting of the cameras and the CAD model, so we had to fix that. Clean up and make the calibration process more comprehensive and intuitive. I'll dive into that a little more in the next couple of slides, and then documentation and have a tentative data set with results that to have a kind of a benchmark to TRON capabilities and accuracies. So as for TRON operation, this is one issue. This is one thing that we want to address when we are building TRON Plus. So we want to be able to have continuous and feasible trajectories on TRON to simulate realistic space flight simulation. And that is a very difficult task because we have a lot of limitations, starting with physical limitations of the room, physical limitations of the KUKA robot arms. So you can imagine how this can become a little tricky when you have some large angles, and another issue is singularities in the motion planning. So we don't have access to the software that finds the plan to get from one point to another, and there's singularities in the middle that kind of make us go from one configuration to another configuration without us controlling what's happening in between. And then currently, Slab doesn't have the capability of commanding the robot every 0.25 seconds to achieve that continuous trajectory that we want to simulate a realistic flight trajectory. So the operational mode, so I'll be talking about the operational mode now, the photo shooting mode. So what we do is we map relative orbital elements to robot commands. And again, we have no idea what's happening in between. That is software provided by KUKA Robotics. So currently we can't simulate realistic flight trajectory, and you can see here in the image that these are positions that intuitively wouldn't make enough movement to achieve what we want if we want to do it smoothly. So we want to be able to achieve a smoother trajectory for these points. So for the operational mode, what we want to do, and this was suggested by Toby also during break. So we we do have ROE to TRON facility global frame coordinates, and we have the inverse kinematics, but we don't have access to them. So what Toby was suggested, and I think that is a good approach, is to try to find those angles ourselves and have control over them, and then we can maybe find feasibility for like a smooth trajectory, and then interpolate those to satisfy the KUKA feasibility. So to not violate the KUKA speed and position limitation. So we don't want to command it too much acceleration at one point. So once we do the inverse kinematics, we interpolate those using cubic splines and check feasibility. And then the collision avoidance is something that Greg and I were working on this quarter to add this feature to make sure that we don't collide with each of the robots, because in the past, robot 2 didn't used to move. So robot 2 is the one on the base, robot 1 is the one that's coming from top. 2 didn't used to move, and we used to kind of have constant linear distance between the two. So when we added, and we want to add this capability, we want to make sure that it's not colliding. So this is something we worked on. And now for the calibration problem. So in the past, what used to be done is, again, robot 2 wasn't moving, and robot 1 was in a constant linear range. And to calibrate for the entire facility, we wanted to have more movement and more coverage in the joint space of each robot, which we didn't have before. And that introduced a lot of bias in the areas that we were moving in. So we want to cover more of the robot positions in the room and in the joint space. We want to have different distances along the camera bore side to have a more accurate calibration of the camera. And here in the 3 images, what we see is, so we use the Churuko boards for the camera calibration, the extrinsics and intrinsics of the camera. And here we see the feature distribution that we predict before taking the images. And this is what we actually get. And that was because of one of the issues I was mentioning before. We had a lot of errors in the beginning of the quarter. So we were predicting this image, this feature distribution. These are these corners. And we're actually getting this in the end. But now we fixed it and we get the feature distribution as almost the same as the predicting. That's just like a little bit of inaccuracies in the robot position rather than the prediction of the offsets. So one of the things that we were kind of bothered with this quarter is that we needed to validate our calibration results. We needed a reference mission, so ROEs, set of ROEs, to validate our mission, our calibration offsets, and the reprojection of the CAD model on the image plane. So we changed that a little bit, and we made we went from the opposite way so that we don't have to have ROEs. So we provide robot positions, and we take from them, we calculate the relative poses, and then we can find, we can reproject the CAD model on top of the image plane rather than have a reference truth trajectory. So we have to rely on that. And then, so the predicted offsets that led to the wrong feature distribution, that's the images I was talking about here. And then again, robot 2 end effector was stationary, so we didn't have enough coverage there in the robot space. And robot 1's range was optimized for the specific use case in the ROEs that we used to calibrate for. So this is also trying to address the issue of not covering the entire room for the calibration process. So we modified this calibration process. So instead of going from ROEs and relative poses, we command the robots now. We tell it what frame position we want, what global frame position we want in the TRON facility to cover the entire space there. And then we tell what feature distribution we want on the image plane. From there, we calculate the robot commands and end effector relative poses. We solve for those offsets, and then since we already have that, we don't need the ROEs to verify, so we can just project the CAD on top of this to verify that our offsets are correct and matching what we see in the accuracies that we receive from the calibration results. So what we want to be able to achieve with TRON Plus will enable, with some software modification, we will attempt to close the loop and have a closed loop capability with TRON and test and validate some of the RPO, some of the algorithms that were developed here in the RPO kit. And then we already have a more comprehensive and more intuitive calibration process that will make it easier for future use of TRON. And then the overall goal is to achieve high accuracy across the entire room rather than just like a very specific range of motion inside the room. So the contributions this quarter, so we regained some capabilities of the lab that we used to have in the lab. So we have that back. We modified the calibration process to, again, be more comprehensive, capture a wider range of both distribution on the image plane and the robot GLC positions, which will help in the robot absolute position calibrations. We modified some of the calibration scripts that we use in lab using OpenCV and other outside resources to comply with industry standards. Thank you, Toby, for your input with the C++ code. We generated a new data set. So we have a new data set that is ready and documented and will be used in the future to compare results. And we worked on a little bit of documentation to make it easier to follow up. And then future work, as I mentioned, we are planning to work on continuous capabilities of TRON and support industrial collaborations and for software and hardware loop simulations and flight testing. I want to thank Greg, Paul, Zara, and Emily for your help this quarter, and Toby for sometimes asking me what I'm doing and make me realize that I should be doing something else. And Professor D'Amico for the opportunity to be part of the lab this quarter. And I'm happy to take any questions.